So welcome back to the second part. It gives me particular great pleasure to introduce the next speaker. It's a very dear former colleague at IIS Princeton, Akshay Venkatesh, where he's the Fernholz Professor in the School of Mathematics. Um, Akshay works many different areas of mathematics. I think you cover quite a lot of the diagram we saw of the mathematical space. Automorphic forms, number theory, analytic number theory, topology. For this, he was awarded, among many other distinctions, the 2018 Fields Medal. And I still remember very fondly the first conversations we had actually in Princeton about AI and math. This was long before LLMs, etc. And so I really look forward to your presentation here. Akshay, the word's yours.
All right, thank you, Robert. And thanks for all coming. This talk comes at the end of this workshop that Lenny talked about at the Lorentz Center here, which was extremely interesting on this topic of mechanized proof. I wrote this talk primarily before the workshop, but I was interested to see how many of the themes that I'm going to talk about were reflected in the discussions of this workshop. So, I can only speak for myself, but I think there's some sympathy for the kind of things I'll talk about in the broader community. Okay, so the title of this talk, I think, is not maybe exactly what I'll talk about, but it was very much on my mind as I was preparing it. And I received an email from a student who's just starting their study of mathematics. And so he says, and I'm quoting this with their permission, I'm an incoming university student who has for a long time aspired to become a mathematician. I believe it would be a fulfilling career path for me. And then he describes various things that he finds beautiful about mathematics. But he concludes with, however, with the rise of AI and formalization in mathematics, I feel like we are destroying the very soul of what I and many others find interesting. Now, AI and formalization are different things. I'll be talking about AI in this talk today. And he went on to ask me a series of questions, and maybe the most important being these. Do you believe that mathematics is worth being studied in a world in which a machine can answer everything for you? And what do you believe would be the job of a mathematician in this world? And maybe the most important message of this talk is that I think we mathematicians need to be engaging with these questions because our students are thinking about them. Okay, well, you may have differing views on how likely some form of this scenario is, but what's most certainly true is I think there are already many students who are worrying about this, and they think, okay, does this career really have a future? And these are not questions, I think, that have an answer, but they're questions we need to be thinking about and discussing with our students. Okay, so that's why I'm not going to answer them today, but I'm going to think about them and discuss them with you. And particularly, I'm not going to talk about so much jobs in the sense of will people pay others to do mathematics. That's a very complicated question, but I want to maybe, I'll say a little related to that, but I want to really start with this first question. Do you believe that mathematics is worth being studied in a world in which a machine can answer everything for you? Okay, so I want to clarify how I'm going to interpret the premise of the question here. Okay, so, we know that there are true statements that a machine can't prove, and complexity theory strongly suggests that there are many provable statements that will be very hard to find a proof of. Now, what's really relevant here is, I think, statements that are interesting for humans and which have comprehensible proofs. But it seems to me at least reasonably likely that there are plenty of human interesting statements of length n, statements that could be interesting to a human being, whose proof, and let me just always understand proof to mean a human comprehensible proof, whose proof takes an exponential length of time in n to find. Okay, so if we accept that, I'm just going to assume that if we accept that so, then if we become 10,000 times smarter, all that happens is the unsolved problems will become a few words longer. Okay? But what is, I think, a feasible scenario is that machines can do everything we can if we're speaking in the, what does it mean? Okay, if we are given a precisely formulated mathematical question, prove or disprove this, if we can do it, then a machine can also do it. Okay. So the first point, the first point that we'll still have open problems and conjectures, I think, is an important one, right? And I think that if a machine gives us a proof of the Riemann hypothesis, I think there will be a first person or first group of people to understand that, and I think they'll be pretty happy about it. I just as you know, we've been happy about other things that we did with machine assistance. You know, we landed on the moon. We didn't walk to the moon. I'm sure Neil Armstrong was quite happy. But okay, so this premise, I think, that a machine can do anything we can, why does it make us nervous? Okay, I think it makes us nervous because we feel, to some extent, we feel that our job is proving theorems. Okay, and I think this is a very diminished view of what mathematicians are actually doing. And what we need to do, so I do think, by the way, we need to engage. I'm not going to get into the question of how likely is this to happen when, okay? But I do think some version of the scenario is likely enough to happen within the lifespan of our students that it's something that we really need to be thinking about. What does mathematics mean? And so I think in order to do that, we need to be looking at all the things we do that go around theorems and proofs. And I think that's actually a lot of what we do. Maybe most of what we do. Okay, well, what is it that we're doing when we do mathematics? And that was a lot of the discussion that went on this week. When you look carefully, it's not at all clear that the central thing is theorems and proofs. And broader than that, I think we have to look at our experience of doing mathematics. Okay, what is the human experience of doing mathematics? And that's something I'm going to come back to as the talk goes on. Okay, so let me just clarify. When I say we, I'm really talking about, there are many, of course, different communities of mathematicians. I'm going to be talking about professional, pure mathematicians in the research kind of component of their lives. Okay, so of course, there are many communities of mathematicians, and a pure mathematician does many things, but this is what I'll be talking about, which I think was the setting of the question that I was asked. Okay, so let me get started by I want to make this point that a lot of what we do comes around the proofs. Okay. So I had the good fortune of working with some very talented young people. And I would say within certain contexts of those collaborations, they were a very good approximation of a machine that could do everything for me. Okay, there was in this thing, there was literally nothing I could do that they could not do faster than me, so I let them do it. Okay? And it felt great. Okay. So we have to think about what was the nature of what we were doing. I think if we were working on a question where the goal was to prove some specified thing, and they did all of it, that wouldn't have felt so good. I would have said, okay, my name shouldn't be on this. But the nature of what we were doing was some kind of exploratory thing. We were trying to take a part of math that wasn't explored, and we were trying to make a good story out of it. Okay? And what does that look like, right? So we would prove something, by which I mean my collaborator, and then we would sometimes I would then realize that's what we wanted, and sometimes it wasn't. It wasn't shedding light. It wasn't a beautiful direction, and so we would go and prove something else. So there was a lot of going back and forth, figuring out what to prove, and then how to weave all these proofs into a story, and that was basically my role. Okay? And it never actually occurred to me, I mean, I'm making this metaphor for this talk, it never occurred to me at the time that I wasn't doing math. Okay, I felt like it never occurred to me. Now, what is important, I think, is that I retained an intuition for the mathematical subject domain. Okay, like I could guess when something would be true. I think if that were not the case, it would have been a very different type of experience. But that was the case, and yet all the proofs my wonderful collaborator did. And so the point of this is to say that there's a lot of that work, and that was all I was doing, was the contexts of these proofs. And I'm going to try to look at that a little more closely by looking at a theorem which we can see in our everyday experience. Okay, and the point of looking at a theorem, the point is not that this theorem is useful, but that its everyday experiences, we can easily look at the context around it. Okay, so we can kind of see what goes around this theorem. I think if you looked at any theorem in math and really looked at how it relates to other things, you would see some version of what I'm about to say. Okay, so the theorem arises from a question, and this is the question: how do you classify symmetry types of repeating two-dimensional designs? Okay, so I took the word everyday very seriously. These are all photographs that I could take in yesterday. Okay, so that's the floor of my hotel room. That's like the fabric of a chair outside the Lorentz Center. That's the speaker in the Lorentz Center, and that's my shirt. Anyway, so these things are everywhere once you start to look for them. Okay, so all right, let me not define repeating two-dimensional designs. You can look at this and figure out what it means. All right, for example, here you have this nice beehive or hexagonal structure. The question is, how do you classify them by symmetry? Clearly, for example, this hexagonal structure has some different types of symmetry to this one. This has some kind of square symmetry. This has some kind of hexagonal symmetry. How do you classify them using that? How many different possible symmetry types are there? And okay, so we can ask a machine this, and I asked some version of this question to a couple of language models, and they told me this answer. There are 17 possibilities for the symmetry type of a repeating two-dimensional design. Okay, actually, there's one on the wall back there. If you okay, the mathematical statement is that there are 17 discrete subgroups of rigid motions of the plane that contain a lattice of translation. So let me unpack that. You take the pattern and you look at all the symmetries it has. So you look at all the ways of either translating it or rotating it like this or reflecting it so that the pattern is unchanged. Okay, and you will get a group of symmetries. They're all rigid motions of the plane, meaning they're composed out of rotations, reflections, translations, and they will be, in fact, a discrete subgroup of the type described here. Okay, and the mathematical statement is there are 17 isomorphism classes of discrete subgroups. So this theorem was first written down by Polya, same Polya of Stephanie's talk. The ideas of it go further back. Okay, the ideas of it were figured out even in 3 dimensions by crystallographers well before this, but I believe Polya was the first person to really draw out the plain version. This is from his paper. It's an illustration of the 17 symmetry types with his notations for them, C, D, and so on. Okay, so that's the answer to this question. And it's a theorem of sorts. It is a theorem. But really, I would say that it's one of many possible answers. Okay, and the reason it's one of many possible answers is it's really answering one of many possible questions. Okay, so if you think about the question of what is the symmetry type of one of these, you, especially if you're not a mathematician, because a mathematician has this concept of group available which makes us leap into this, but you quickly realize there are actually many possibilities for things you could include in that. Okay, what is a symmetry? I think there are designs that a ordinary person might call symmetric, where the symmetries are not rigid motions. Okay? What is equivalence? I said there are 17 isomorphism classes. Right? Now, if a mathematician hears that, they already think there's something a bit strange about that, because that might not feel to you like the right notion of equivalence, and there are a priori different things which you could do. But then you get to more interesting things. If you have a colored pattern, like if you take my shirt from the last slide, does the color matter? Okay, does just the pattern matter or the color? Okay. If you have a pattern with little elements, are you keeping track of how those elements interact with the symmetry group? If you have a pattern with many tiles, you can ask, are two adjacent tiles, are they reflections of each other or rotations or glide reflections? So these are, so depending on the question you will ask, you will get a different answer. And not only could you ask the question, people have asked the question. And there's this beautiful book called Tilings and Patterns, which is several hundred pages long, which goes through many different ways you could think about what you mean by the symmetry type, and you'll give a collection of different answers. It's not always 17, and the classification is sometimes much more elaborate. Now, let's assume we settle on a question, okay? So we agree that the symmetry type of a design is what I alluded to on the previous slide, which is the symmetries that carry the pattern back into itself, the isomorphism class of that group. Then, now, one reason I picked this question is that it's very interesting because it's sort of it's a natural experiment because there are many different communities of people who have thought about it, and they all pick different notation. Okay, you can say those 17 things. I showed you Polya's notation. It's one of at least 5 different notations, I think. And those notations, again, reflect different things, to some extent, different emphases when you look at a design, right? You could look at it and first look at the underlying lattice of translations, or you could look at it and first look at the smallest order rotation you have. Okay? So there are many different ways, and it's not entirely easy to translate between these. I mean, of course, it's not hard either, but it's not something, if you're just sitting and thinking, you get confused faster than one would think. And I think it in part reflects that the different people who thought about it had really different goals, right? So an artist might want to make such a design. There was also archaeologists who were interested in the question of how to classify artifacts according to the symmetry types of the design there. Okay, and that's a different question to what a chemist or a mathematician might want out of this classification. Okay, and then once we figure out a language to express the answer, one might ask for a proof, okay? And then you again have the choice that there are really many different proofs, right? You could give a proof, you could give a proof that's entirely group theoretic. Okay, you first classify the point group, and then you classify extensions. You could give one which uses the classification of surfaces, where you take the quotient of the plane by that symmetry group, and you then classify it as an orbifold. You could start with the lattice and then do some kind of more or less ad hoc reasoning. There's a paper in the 1930s in the Journal of Textile Analysis, which essentially argues this. And in place of where I would use, it never says the word group. Okay, and where I might use group theory, it substitutes in some arguments of Euclidean geometry. Okay. So even in this, and this is the choices that are going on here, I think they require a good amount of mathematical sophistication to either to make them or even notice that you're making them. Okay, and so these are all the choices that go in sort of going from the natural version of this question to the mathematical one. So let me just say something about the experience of doing this. So I spent quite a lot of time on this last week. And so what I was doing is, even though it wasn't really necessary for this talk, I was trying to understand the classification. So that means that I eventually had to put it in a form that wasn't quite any of the standard forms, but that was very well adapted to how I think about it. Okay, and I found that process very satisfying. Okay, the math is old. All right, it was known 100 years ago. It doesn't really matter if it was known 100 years ago or a machine did it. I would have still found it satisfying. I found it, I think, just as satisfying as a week doing research. And because I think, like many mathematicians, what I'm really appreciate is the personal experience of mathematics. Okay, I have to personalize this result and align it with the way I think so it feels effortless, and that I think is different from, in this case, none of the classifications really matched the way I like to think about things. Okay. So as I said, I don't think this is an isolated example. I picked this one, it's easy to talk about, but if you look at the history of many sophisticated mathematical results, and I'm not a historian of math, but I've done so in a few instances, and I've always been struck by how much it changes over time. Okay, and when I say it changes, everything changes. So it may, in some sense, it's sort of the same. You could think of it as equivalent from the mathematical point of view. But the way the question is asked and answered, of course, change. But not only that, everything around it changes. The definitions change, the concepts that are used to express things change, the notations and the heuristics and diagrams, all of these change. Anyone who's had the experience of reading original math papers will, I think, relate to the fact when you read original papers, you almost always get something out of it you didn't know. Okay, and the reason is that as these things change, I think they're not really approaching some better form. There are different ways, and they give you different things. Okay, so usually when we replace some original argument with a new one, it's better for some purpose that we now deem to be what we want, but we also throw away something that the original argument was good for. Right? So there are many, many different, infinitely many ways to think about the same piece of mathematics. Right? I think that's this is really an essential part of mathematical practice. Right? The fact that this is so. So going back to the theme that I mentioned of, the same way if multiple people can see an event and describe it in completely different but factual ways, there are many different ways in any that we can express the mathematical world. I don't think there's any best one, right? In the end, the choice that's going on, I think they are about what we want. Okay, of course, you could ask. I mean, in the previous case, the large language model made the choice for me, but I don't think we should want a machine to tell us what we want. Okay, that's something that we want to be choosing. Not only does it tell us what we want, it helps us discover what we want in the process of thinking about it. Okay, so you can't choose between these many different ways without some understanding of what you want out of the whole thing. And if we think about doing this kind of mathematical storytelling with the aid of one of these machines that could prove things more than me, I really don't see why it wouldn't be an interesting profession, so long as I said in the interaction with my collaborators, so long as we insist on retaining a direct experience of the mathematics. Okay, I don't think anybody wants to be pressing a key and watching the machine do things that you have no understanding of. Okay, but if that's the case, I really don't see an essential tension between having a machine do proofs and what we find valuable in math. Okay, I want to have a little aside here, which I think is an interesting point to bring up in this around this point that there are many different proofs. So in his 1900 ICM address, Hilbert proposed these 23 problems, but there was another problem that he considered putting in there but didn't, which was discovered by Thiele. And this 24th problem was, I'm just going to say it in my words. Okay, Thiele has a nice article about this, but the way I read it is that Hilbert wanted to study the space of proofs for a given result. Okay, he said a result goes from here to here, but there are many ways of going from here to here. And he was interested in two features. He mentions being interested in two features. The first is, what is the simplest? I don't know if he says simplest or shortest, but something like that. And the other is if he wanted to know if you have two different proofs, and now I'll just use my language, can you kind of homotope one into the other? Okay, can you find a way of expressing whether two proofs are sort of essentially the same or not? I think that's an interesting thing for us to think about since we may have the possibility of producing many different proofs for the same result. But I think the way we should think about it is not in terms of the simplest proof, but again, different proofs give us different types of understanding, and that is something that we should understand the space of proofs with that in mind. So the space of proofs is, for me, a psychological object, not a formal object. Okay, so far I've talked about my own experience, and I've said, okay, I personally would probably be fine with having a machine that could prove everything for me. But in the end, and I'm not going to explicitly talk about jobs, but I think this is the underlying question of that. If mathematics should exist in a meaningful sense, it has to have some value to non-mathematicians. Okay, it should have some value to someone who is not a professional mathematician. And so I want to at least look a little bit at that. So I think a very large part of our argument about this lies in the use of mathematics for science and technology. Okay, and I think we can all agree on that. I'm not going to talk about it. I do think it's worth thinking about. I don't think we can assume that that relationship between math and science and technology remains the same, okay, in the kind of scenario we're thinking about. But I don't want to talk about it, okay? What I want to look at is what you might call the kind of direct value, okay? So why is the experience of doing math valuable? I've said I enjoy the experience of doing math. Why is it valuable to a non-mathematician? Okay, not because it's useful for any other purpose, but simply as an intrinsic experience, what makes it of value? And there are a couple of answers that I find compelling. So I think these are worth much more discussion than I'm going to give, but let me say them. So first of all, mathematics can give us internal certainty, right? That is, people understand when you say 2 + 2 = 4, or you learn that a triangle with 2 equal sides has 2 equal angles. You can have a kind of internal certainty about that. It's not dependent on the external validation or the outside world, right? So there's something which I think is miraculous about that, and I think so that's something people have always found a little miraculous, that you can have internal certainty of that type about anything. And I don't think that feeling is going to go away among humans. I do want to say, when I say internal certainty, that's a different thing to the feeling that we get out of mathematical proofs that we might find in a math paper. Many of our proofs and papers are long, complicated objects, right? And I would say for many of them, you don't have that sense of certainty that you can get out of a proof. Similarly, the fact the proof is formally correct is not what I'm talking about. I'm talking about the psychological experience of proof here. So that is, I think, an experience that's really a unique one for humans. The second one is that mathematics is, of course, an exact language, both for talking to ourselves and to others, right? So in reading some of these archaeologists talking about why they use symmetry to classify designs, I was struck by the emphasis on this fact, the utility of, if you see a hexagonal pattern, two people can agree that it's a hexagonal pattern in a way that they can't agree that the color is bluish, right? So the mathematical language, when we can speak about mathematics and you and I can have in some sense exactly the same understanding of what the words mean, in a way it's very difficult to achieve in natural language. Okay? Now, that's, I think, evidently useful for science, but I think it's also, really a social function, right? To the extent that we need to communicate precisely, here I'm talking about mathematics in the broad sense, okay? I'm not so specifically academic mathematics. When we need to communicate about things very precisely, it's almost inherently mathematical. Many of the ways we use numbers, as I see it, are not really about the world being intrinsically numerical, but because the number has the same meaning for you and me. Okay. So these are very important. I want to emphasize something else, though, which is that mathematics is a form of play. And of course, that's not something you might want to, we feel hesitant to say that, right? Because it sounds frivolous. But if you think in terms of intrinsic value, I think play is outstanding example of what has intrinsic value, right? Children, you don't need to pay your children to play. You don't need to tell them that it will, do something else. It's very hard to stop them from playing. Right? So the mathematics has always been, I think, has this essential component of play. So here are Archimedes on the left and Fermat, who, as I see it, were playing with their contemporaries, and they were playing with exactly the same question, okay, a couple thousand years apart. And maybe if I'm meant to be talking about non-mathematicians, but Fermat was not a mathematician. Okay, mathematics was entirely a hobby for him. He managed to found modern number theory. And the modern there are plenty of modern successors to this. So on the right here, this is the mathematical games column, which ran for decades in Scientific American. Okay, and some of you may have read this. It was written by Martin Gardner, and it really set the standard, I think, of recreational mathematics in the United States for many years. It's a wonderful column, and what is striking, I think, is just how popular it was. It was so popular that they moved it from the end of the magazine to the front. Okay, the front of a magazine called Scientific American is Mathematical Games. And on the left, I think the kind of modern successor to this is, we can see it if we look on YouTube, and there are these astounding videos of expositing pieces of fairly sophisticated math, which are getting millions of views. Okay, so of course, these people are not watching these videos because they need a grade, right? It is a recreation. And this video is by one of the very talented creators of these, Grant Sanderson. It's called "What Makes People Engage with Math," and it's quite interesting to watch in the context of this discussion of what gives math intrinsic value. Okay, so now I have to say some harsh things. So I have to say that the kind of image of math that I've shown you in these slides, I find it very difficult to recognize in the practice of academic mathematics. Okay, and I'll give it let me skip forward to give you an example of what I mean. So, for instance, we often say we value understanding, and this was mentioned many times this week in this workshop. Okay? But our record on this is terrible. Okay, like nobody no non-mathematician understands what mathematicians are doing. It's not even that they don't understand the answers, they don't understand the questions. And what's even worse is within mathematics, for a typical, we give a talk, outside of very narrow fields, we have no understanding. And in the rare case we can even understand the question, we have no idea why someone would be interested in it. Okay, and that is, I think it's very clear that something has gone wrong. And I don't think that's, I more and more think that's not just me who feels that's the case. over the week, I talked to many people who felt that way. There's some essential gap that has opened between our, the practice of mathematics and our values. And for me, what has this comes from is we focus on theorems and proofs. It's the same issue that we have to address, I think, also for AI. We think of ourselves as producing theorems and proofs, whereas the value of those things lies in the human experience of them. We don't discuss the human experience of them. Okay? And that, I think, has led to this situation, which many of us find deeply dissatisfying. Now, the reason I'm bringing this up now is that I think it's an appropriate time, because AI, I really think, is it will really transform not just mathematics, but all of academia, because it will change how people think, right? Just as writing changed how people think, AI changes how people think. And so we have to really rethink what it means to be a scholar, right? And that goes for math too. So no matter what, I think the field of mathematics is going to be completely transformed in some way or the other over the coming decades. And so I think we should take that as an opportunity to really think about what we want and realign the subject in that direction. And I think we have a possibility to move the field in a way that's not just more enjoyable for us. Of course, there are very few of us, but also it's more valuable for everything, for non-mathematicians as well. So, yeah, I think this is happening, as I said, whether or not we think about it consciously, and it will be better to, it's better to think about what we want and talk about what we want and talk about it with each other and our students. And, I don't think we can hold on to specifics, okay? If I don't think we can say, for instance, that, well, I hope that people will remember what algebraic K-theory is in 50 years or something like that. They may not. I don't think that's the kind of thing we should cling to. What we have to do is look at what's valuable about mathematical practice and try to preserve that. And I want to finish, since I said some harsh words. Of course, I wouldn't be talking if I didn't think there were valuable things about mathematical practice. So let me give you a couple of things that I hope we can preserve as the field has changed. So one thing I feel really grateful for is that I was allowed, when I was younger, I spent years kind of immersed in thought about this one or the other deep question or idea. These questions were kind of far beyond me and you would spend a couple of years and you would understand a tiny bit. Right? But that's somehow that experience of sustained attention, I think, is a really wonderful one. Right? Nobody came and said, you need to write papers every 3 months. Nobody came and said, nobody is working on this, it's uninteresting, you should do something else, although in fact nobody was working on it and nobody considered it interesting. But nobody said it to me. And nobody said this is useless. And I think that is a really valuable thing. Well, it's because we take, I think, a long view of the mathematical discipline. Like, we remember that there was as a culture, and maybe not in an individual sense, as a culture we remember there was mathematics 1,000 years ago, and 100 years ago, and there'll be mathematics in 100 years and 1,000 years. And so we allow our space to think in a way, space to think about things that are separated from the needs of the immediate moment. Okay, so I think that's a very valuable, this experience of long attention is valuable, this long view that we have in our culture is valuable. So these are among the things that I hope we can preserve in the decades to come. All right, thank you.
Thank you, Akshay. So before we go to the panel discussion, perhaps one or two direct questions for him. Yes, please.
Yes, hi. So I want to suggest something that I think really aligns with the point you're making, which is the
Yeah, I think, and not just reproving a given theorem, like somehow transforming the way it's stated. I do think, I don't have any systematic way of thinking about it, but I think it's an essential part of mathematical practice.
And I agree that the new proof should be interestingly different from the one that's already there, right? Which should kind of give you some new insight. And that's what really matters about the new proof.
Yeah, the experience of the proof is what matters.
Other questions? Yes, Michael.
Starting from the experience of the student and why that student was concerned about the loss of interest of the discipline, you have to say that this is based on a story that's being told by the industry, and we saw it illustrated in all those magazine covers, that it's going to be, that they're going to be taking over the practice of mathematics. Now, we saw a version of Google's project of Google that is presented as a gift to mathematics, but Google has many tentacles. And two other mathematics projects were headed by people who, one of whom, I won't mention their names, one of whom explicitly said that the aim was to solve mathematics, and another one who said that, and I heard this in a public lecture, that when the technology solves mathematics, mathematicians will have to find something else to do. So that's the narrative that's being promoted. It's being promoted with a massive public relations apparatus. And why, and what can be done, you think, to overcome the impression of mathematics that's being given by the industry?
Well, I think our role is to focus on, like in part the image the industry and the world have of us are images that we ourselves represented, and I think we should be working on that. How, we need to articulate what it is which is important and valuable to us more clearly than we do.
Yes, one, Emily. And then I'll go to the plenary discussion.
So I've sometimes heard Hilbert's 24th problem described as a problem of simplifying proofs. And you pose this question of how little mathematicians even understand each other.
Yeah.
Is there a way to approach that question of better communication, better understanding between mathematicians, beyond mathematicians, aside from the idea of just trying to simplify proofs?
Well, I think, so this may not answer your question, but I think, we have to ask, why are we proving things at all, right? And for me, the answer to that is entirely in the experience of them. That the proof and the theorem is a means and not an end, right? And I think simply having that shift of perspective would be useful for us.